file in the container, which is there. So you can open that up and follow along, but I'll kind of show the slides and we'll kind of work our way through and see what's going on in this program. So at the top we have a couple of definitions, which are sort of just like abbreviations. As we keep going, they'll make a little bit more sense as to what these are for. The main thing that we're going to be defining is a function that's called read input. So it's going to read some information from the user. And there's two local variables here. The first one's called buffer. And what this is saying basically, if I can get a little pointer here, it's saying that it consists of chars, which are characters, right? Letters, numbers, and so on. And these funny brackets and the buff size thing mean that it's an array that's buff size long, and the definition of buff size is up at the top of the file, 128. So basically, buffer is 128 characters, or it's space for 128 characters. So in C, that is how you allocate space for a string. It's basically just an array of characters. The second thing here, it's a constant. It's a constant integer. It's called I don't change because I really wanted to emphasize that it should not change. It should always be the same value. The value that we're setting it to, some number in hex, it doesn't really matter so much. The point is that whatever we set this to, it really shouldn't be changing. And I guess I will give you a spoiler alert, and it actually will change. So anyway, kind of the main part of the program, we're going to tell the user, hey, give me a line of input, and we're just going to repeat it back to them. And we're going to use a function that's called get in C. Out of curiosity, who's used gets in C before? Okay, so some people. It's kind of infamous, so if you've heard of it, you probably know what's going wrong already. But basically what gets does is it will read an entire line of input from the user. Okay? And then it's going to put it into the buffer that we're passing to an argument. So the problem here is that it will read a line of input no matter how long it is. Right? It could be super huge. The way that gets is, it's supposed to work is, right, we have this line of input that we're giving to the program. We have our buffer here. And it puts it into our buffer and it kind of just sits there, right? And it's nicely contained inside of the buffer. But obviously the problem is, what happens when we have a line of input that doesn't fit inside of the buffer? Right? So if you're used to like more modern languages, then you'd say, well, the buffer would grow or, detect that something went wrong and it would stop. Well, it turns out that the get function does none of that. It actually will just write that line of input into the buffer. And it turns out whatever is after the buffer is going to get clobbered. So that's not so great. And this is basically visually what a buffer overflow is, right? We have this buffer, this area of memory that we've kind of earmarked for a certain purpose. In this case, is to hold a string. And we try to put something into it that doesn't fit. And so we end up going past the end and messing other stuff up. All right? So that's a buffer overflow. Hey, I didn't put it in the slides. So the rest of this program is basically going to print some stuff that just helps us get a feeling for like what's going on after we have that overflow. So we're going to print a bunch of information. You don't have to worry too much about like the actual syntax here, but we're going to print the string that the user typed. We're going to print the address of the buffer, where it's living in memory, and the length of the string, and the size of the buffer. The size of the buffer should always be 128 bytes, but maybe we're forgetful. And anyway, it's good to have everything there. So we have two checks in the program. They're pretty simple. The first one's just checking if the length of the string that the user typed is greater than the size of the buffer. Right? So this is basically just an easy way to say, hey, that's probably not good. I tried to put this much stuff into something that's smaller. Maybe something bad can happen. So when that happens, we'll print a message. And then the other thing, which I kind of revealed the spoiler on already, is we're going to check for some reason, I don't know why, we're going to check to see if that constant value changes, because who knows, maybe something crazy will happen. So if that constant value does actually happen to change, we'll print a message and say what it changed to. All right. So kind of the first thing we need to do here if we're going to play with this program is we need to make some big strings. So rather than hitting like the A button, 128 times, we can use Python, or there's a number of ways that you could do this, but I'm going to use Python. And basically this command says, take the string that's just A and repeat it 128 times, and then print that out to the screen. So we'll do that real quick. So can you guys read the console, or should I make it bigger?
A little bigger.
A little bigger. Okay. Oh, all right. Is that good? Or bigger?
That's good.
That's good.
That's good? Okay, cool. All right, so we will print A, and we'll do asterisk 128 to repeat it 128 times. And we can run that, and voila, there is a string of 128 A's. So the next thing that we're going to do is we're going to use a feature of Linux that's called piping, which is basically this symbol with a vertical bar. And it basically says, take the output from the program on the left, so that's obviously going to be a bunch of A's, and send it as input to the program on the right. And the program on the right is going to be the exploit me program, which is just the C program I showed you, compiled into an executable. So if we do that, it runs. You can see it's repeating back the string that we said. It's telling us what address the buffer was at, and the length of the string, and the size of the buffer. All right, so this is kind of the non-interesting case. So now what we're going to do is we're going to try some longer strings, right? Strings that are not going to fit into the buffer, and we're going to see what happens. And since I've done this a whole lot of times, I happen to know kind of at which points interesting things start to happen, and it's at these lengths. So we'll kind of just run through these, but you can experiment with these or other ones if you want. So basically at 128 bytes, nothing too interesting is happening. But if we go up to 132, we get this message that we've overflowed the buffer, right? Because we've given it a string that is 132 characters long. That obviously doesn't fit very well into a 128 byte buffer. But nothing else has happened. So let's make that a little bit longer. Go to 136. Still overflowing the buffer, nothing else happening. We'll go up to 140. And now we're overflowing the buffer, and as I've already spoiled the news, that constant value that should never ever possibly change, all of a sudden changed. So that's kind of weird. Turns out that if we keep increasing the size here one by one, if you watch this value that the variable is changing to, that will also change every time I increase this length by a little bit. You can see that changing. And eventually, it will get to this value, which is the final value. And we can basically keep increasing the length again, and nothing changes. So kind of weird. I'm going to jump up to 151, which I just happen to know is the last length where nothing changes. And then we will go to 152 A's, and kaboom. So this is kind of melodramatic, but this is actually the program crashing. It's saying illegal instruction, and then the operating system's killing the process. So the program has actually crashed here. And if we make it bigger again, now we're crashing again, but we're getting a different error. We're getting a segmentation fault. And it turns out you can continue making bigger and bigger inputs. Here's a whole lot of A's. That still results in a segmentation fault. So what happened here? So if we don't overflow anything, nothing too surprising. The program runs as expected. From length 129 to 139, we're overflowing things, but otherwise we don't really see any sign that something's going wrong. At 140, we start to see the I don't change variable start to change. And as we kind of keep going larger and larger, we see more changes. And then for a period, there's no changes again as we get larger. And then we see two different kinds of crashes. So what the heck is going on here? How many people are surprised by what's going on in this table? Like have no idea what's going on here? Really? Only 3 people. All right, that's better. All right, so you didn't raise your hand. What's going on?
So overriding awareness, variable I don't change.
Okay, but why don't we see anything happening from like 129 to 139? Like,
I guess a little cushion space.
cushion space. All right. So apparently people are onto me here. They came in with background. So you might be right. We'll see. Yeah. So anyway, there's a lot of weird stuff here. I thought more people would be surprised, but yeah. It's kind of weird to me, that you have this buffer and then you can overwrite past the end of the buffer and like for a while nothing happens. It's kind of weird. Then we end up overwriting, presumably something ends up happening that's writing into that other variable. We see these weird bytes getting written, 0041. What are those? Another thing here where we're kind of increasing the amount of data that we're writing. It doesn't seem to have any effect. And then finally we have these 2 different mechanisms where we're crashing in different ways. So to talk about why this happens, we have to talk about kind of some of the magic that goes on under the covers when we're dealing with local variables. So here's the 2 variables that we've been dealing with, our buffer and this I don't change variable. And a very simplistic view of memory in the computer, we can look at something like this. So there's different regions of memory, there's the stack, there's the heap, different parts of code. And we're not going to talk too much about that other than to say that these local variables are going to live on the stack. And at a high level, that's because the stack is used to represent things that are related to function calls. And local variables are, local to a function. So it kind of makes sense that they live on the stack. So if you look at the stack and you see what's in there, it mostly consists of stack frames. So each function, when it runs, has this area of data called stack frame that has certain information in it. Usually starting with the first function in the program. So in C, that function is called main. I didn't show that because it's pretty boring in our case. But the main function calls the read input function that we've been talking about. So let's talk about what goes in one of these stack frames, or specifically for that read input frame. Because that's going to explain a lot of the strange behavior that we saw. Well, the first thing that is a part of the stack frame is something that's called the saved return address. And it turns out that's going to be really important. And basically what this is used for is, when a function finishes executing, it has to go back to the function that called it. And how does it know which function called it? Well, the address gets stored in the saved return address. So this is basically the mechanism that functions use to return to their call. The next thing in the stack frame is something called the saved frame pointer. I'm not really going to talk too much about that, but you can think of that as being the kind of the start of the frame, the official start of the frame. And there's going to be these offsets to the left of these boxes, basically saying what is the offset from the frame pointer to whatever that box is holding. So it's kind of a way that we can talk about where the frame begins and kind of say where a variable is or some other box in relation to that. All right, so one of the things that probably won't surprise you is that, of course, we have some space for the variables, our local variables. So the first one that we happen to have here is the I don't change variable. It's 4 bytes, it's large, it's at offset -4. And then the next thing we have is some padding, which is what you suggested might be going on. I'll explain in a second why that's there. But this doesn't correspond to any variable that we have. It turns out it's something that's automatically added by the compiler. And then finally, we of course need to have space for our buffer, right, which is 128 bytes. So why is this padding area there? To make a short story of it, some data types need to be aligned to certain multiples of addresses. So this buffer, which is a string, it turns out has to be aligned to a 16-byte boundary on this particular machine that I was using. So what that means is that it can live at an address like 0, 16, 32, 48. You can keep going until you get to the end of memory. But you couldn't have it at address like 3, or you couldn't have it at address 5, because those aren't multiples of 16. And the reason for that is basically for performance. There are some things that you can do to write faster code as long as you know that something is aligned to a certain boundary. So that is why the padding area is there. So let's go back a little bit and let's revisit some of these weird things that were going on, and let's see if we can maybe explain them now that we have this understanding of what the stack frame looks like. So the first thing that I thought was kind of weird was, why don't we end up overwriting or changing that I don't change variable from 129 to 139 bytes? And basically what's going on here, if you want to think about it from the perspective of the stack frame, when we put our input into the buffer, we're starting at the bottom. So we're basically going to have our data that we're entering start at the bottom and start filling things up. So obviously if we only have 128 bytes, everything's going to fit inside of that buffer and everything's going to be awesome. But if we keep going, now all of a sudden we start to overwrite that padding area. And if you, of course, add the sizes of these things together, collectively they're 140 bytes. So basically what's happening is that we asked for a buffer that was 128 bytes, and we got one that was 140 bytes for free, basically because the compiler had to do something to make sure that the variables aligned. So it added a little bit of extra space for us. So basically we got lucky. So that's the first mystery, basically. We're writing into this little wiggle room that gets added from the padding. The second mystery, what is this 00 byte that we're doing that's overwriting the I don't change variable? I'm willing to bet someone in the room already knows the answer to this. Does anybody know?
String terminator.
String terminator, that is correct. So in C, strings have a byte at the end of it. It's called a null byte. It's basically just a 0 that indicates the string is over. Right? It's the end of the string. And so what we're actually seeing there, when we see this 0 getting overwritten, it turns out that's actually the byte after the input that we entered. And so one of the weird things that kind of happens in C is that if you have a string that's 5 characters long, like hello, you actually need 6 bytes to store it, because you need 5 for the characters, and then you need 1 at the end to represent the null byte. So one thing that can happen is you can have these off by 1 bugs that are kind of weird. If you were paying really close attention, you probably would have noticed one of these already, but I kind of just waved my hands around a little bit to avoid talking about this until now. But if you were paying super close attention, you would have noticed this. All right, next question. What is the 41 byte in hex? I'm also going to guess that someone knows the answer to this, so I'll throw it out to you guys. Yeah?
Is that a capital A?
That is a capital A in ASCII. That's correct. So, so basically when we type something, a message, and it gets stored in memory, we have to encode that somehow into bytes. And so C, we're using ASCII encoding. And capital A happens to get mapped to the number 41 in hex. So just as an example, if you have the string A, B, C, D in lowercase, it would map to 61, 62, and so on. You can probably figure out how the rest of the alphabet is represented in ASCII. And of course, we need to have that null byte at the end. And capitals are just slightly different. So again, the 41 byte that we're seeing getting overwritten is actually the capital A byte that we gave as input. So if we changed our input from like capital A's to capital B's, for instance, we would see a bunch of 42s there instead of 41. All right, fourth mystery. Basically, why don't we crash until we get all the way to having 152 A's, right? Which is obviously quite a bit larger than 128 bytes that we allocated for the buffer. Well, again, going back to the stack frame, what happens as we kind of keep writing? Well, we're going to overwrite the idle change variable. We kind of already saw that because its value is changing. And then we overwrote that saved frame pointer, which it turns out in this case doesn't really do anything too bad. And that gives us another 12 bytes of wiggle room. Now, after that 12 bytes, we end up starting to overwrite the saved return address, right? So, what do you think is happening when we return from that read input function? It's going to use whatever address is stored in that box. So as soon as we start to, overflow into that box and change it, bad things start to happen. And so that's why we start to crash. Now, why do we get two different error messages, essentially? Two different ways of crashing. And the answer to this is that when we have a string of 152 characters, right, remember we need to have the null byte. So we're actually going to write 153 bytes. And that means that we're going to overwrite into the saved return address just a little teeny tiny bit, right? One byte. So we're not going to overwrite the whole thing, we're just going to change one byte in that number. Now, to talk about what that means, we have to talk a little bit about endingness, which basically means how do you interpret values in memory when they're more than one byte? And there's basically just two ways that you could do this. You can basically put the little end of the number in memory at first, or you can put the big end. And so the way to think about this is, when you write a number down that has multiple digits, right, we know that the least significant digit goes all the way on the right side, and the most significant digit goes all the way on the left. Well, you can basically extend that idea to bytes that are represented in hexadecimal too, and talk about rather than the least significant digit, there's the least significant byte. So the least significant byte is called the little end of the number, and the most significant byte is called the big end of the number. So basically, on Intel machines, which is what my machine is, and probably whatever, I'm sure it's on whatever cloud environment GitHub is using, it's a little endian machine. And so that means that the little end of the number is stored at the first or the lowest address. Another way to think about this that might be a little bit easier is that it's kind of backwards from what you're expecting. So if it was a big endian machine, you would probably just not even think about this and it would work. Turns out a little endian machine is kind of the opposite of what you're expecting. You kind of write it in the reverse order as you would write up a number normally. So what does that mean if we overwrite one byte? Because it's going to be the lowest byte in memory, the lowest address, or the first address, it means that the change is going to be not that significant, right? It's going to be a small change. Obviously, ideally, you would not overwrite the saved return address at all, but if you had to choose between a non-significant change and a significant change, I guess it's better to have a non-significant change. And that's what's going on here. What byte are we actually writing in the saved return address?
Null byte 0.
The null byte, 0, that's right. Yep, because the last byte that we're going to be writing is at the end of the string, and so that's a null byte. Didn't even need the hint. All right, so here's going to be our first demo. And basically what we're going to do is we're going to run this in debugger, and we're going to look and see that we're changing the saved return address. So these are mostly here if you're trying to follow along. Hopefully you have the slides open and you can basically type this in. I'm going to mostly try to do this from memory, and we'll see how that goes. So the first thing that we're going to do is we're going to create a 152 A's, and we're going to write that into a file that I'm going to call input. And if you want to, you can find that file and you can open it up and you can verify that it's a whole bunch of A's. All right? Super exciting. All right, now we're going to use a debugger called GDB. This is a debugger that works for executables, and it will allow us to basically stop the program at different points and kind of inspect what's going on. So the first thing that I'm going to do is put a breakpoint in the read input function, which is where all this magic stuff is happening. And then I'm going to say to run the program and pass along the input that we put into that file, which is a whole bunch of A's again. So if that works, now we are at the beginning of the read input function. And so we can use a command called info frame. And this will tell us a whole bunch of fun information about the stack frame. And if you look here where it says saved RIP, that's just another way of saying this is what the saved return address is. So this number here that's ending in AE is the saved return address, and this is before we've had the buffer overflow happen. So the next thing we're going to do is, I happen to know exactly which line the buffer overflow is, and if we use this command until line 16, it's going to go after the buffer overflow. And if we run that command again to take a look at the saved return address, we can now see that that least significant byte has changed from AE to 00, right? Because we overwrote that with the null byte. And if we use continue, that basically just says keep running as long as you can. We'll run, and then the program receives this signal illegal instruction. So what's going on when we get that signal? So this is kind of a funky looking command, but what it's doing is it's asking the debugger to look in memory at what code is supposed to be executing and tell you what machine code is there. And you can see it says bad, which basically means it's gibberish, it's not a valid machine code instruction, and that's exactly why the program ends up being terminated. In contrast, if we took the original value and passed that in, we get something like this, which is a machine code instruction. So basically what's happening is we overwrote the return address. We ended up trying to execute the code at that modified address, and while that was an address in memory, it turns out it wasn't legitimate or valid machine code, and so we crashed. So that's what's going on when we have length 152. Why do we get this different error, right, in the other cases? And so we'll do this a little bit more quickly, but we'll go back and we'll create an input file that's 153 A's, and we'll run that in GDB again. This time we're not going to set any breakpoints, we're just going to see where we end up. So we run, we crash, we're getting that segmentation fault error. And this is the address that we end up in. Right? So we've basically overwritten the two least significant bytes there. And if we use that same command and we ask the debugger what is the machine code at that address, it turns out there's nothing there. So in the earlier case, we were pointing at some memory, but it wasn't valid machine code. Here we've actually changed the address so much that we've basically gone out of the area of known memory. And so visually it looks something like this. So all the memory addresses that we're talking about right now are in this memory segment that I just call program code. It starts at this address, and the original address that we were supposed to return to, right, is somewhere in the middle of that region. If we overwrite that one byte with a 0, what we're going to do is we're effectively making that address a little bit smaller, right? So we're kind of moving it down closer towards 0. And when we overwrite 1 byte, you know, it's just a little bit. So we're still in that realm of the program code memory segment, but it happens to point to gibberish. When we write more than 1 byte, or overwrite more than 1 byte, now we're actually making it even more smaller. In fact, it's so small that it goes before the start of the program code in memory, and that's why we get that different error. So that was a whole lot of detail on what's going on in those cases. Why did I talk about that when this is about exploitation? And the reason is we really have to understand all the weird behaviors of the program at a very, very low level to be able to kind of use that information to our advantage. All right? So now that we're all professionals and we know this program inside and out, we're going to start writing our training wheels. Right? We're going to make an exploit. This is going to be a slightly easier one. And what this exploit is going to do is we're going to execute a function that's already inside of the program, but that should not have normally been executed. All right? So it turns out in that same program we've been talking about, there's another function that I just didn't show you. It's called goal function. And all it does is it prints a message to the screen, right? Basically telling us that, that we called it. And we haven't seen this message, and the reason why is that this code is in the program, but we never called it, right? So basically under any normal circumstance, we should never see this function execute. And what we're going to try to do is we're going to try to find an input to the program that's going to make it call this function. So that's kind of our first goal. So it's kind of a recap of what we've been talking about. We've been talking about the stack frame and basically giving input. And obviously, you know, the more input we give, the more stuff that we start to overwrite. Well, another way to think about this is that, you know, we're overwriting things, but we also have control, right? We can control what values are going into each one of those boxes. It probably won't surprise you too much to know that the saved return address is a really important box to control, right? We already saw that we can crash the program if we put the wrong thing there. But what if we put something there, you know, that is quite helpful, right? Like what if we put the address of that goal function, right? That seems like it might be a good way to accomplish our goal. So basically the way to think about making this exploit is we're sort of creating our own stack frame as an input, and then that stack frame is going to be copied on top of the real one. And obviously because of the way that saved return addresses work, eventually control flow is going to be transferred to that modified address. So that's the goal. We already know it's 152 bytes from the start of the buffer to that saved return address. So we kind of already know how to do the first part of this, right? We make 152 A's. So that's kind of one half of the problem. The second half of the problem is we need to actually put the address of our goal function. And of course, to do that, we have to know what that address is. So there's a couple ways that you can get this, but we'll just use GDB again to basically ask it what is the address of the goal function. And actually, since it's still running here, I think I can just ask it. And yeah, so I just used the existing GDB session here, and this highlighted thing, the number starting with a bunch of 5s and ending in 5282, that is the address of our goal function. So that's where we're trying to get the program to go to. Okay, I have there the slides. All right. What we're going to do next is we're going to create a Python program that's going to basically figure out what bytes the program should see, and then it's going to write them into a file. And the reason that we typically do things this way is because we're often dealing with weird bytes, right? So bytes that have no printable form, right? So if the byte is like, 3 or A, that's no problem. We can just write that down. But it turns out that when we talk about like byte 0 or byte 01, things start to get pretty weird if you do things like try to copy and paste them. And so it's generally better just to write all this stuff out to a file. So that's what we'll do. If you're kind of playing along with the dev container. This is in there. It's called trainingwheels.py. Now I'll walk you through the steps of the script. So the first thing is we're going to create our 152 A's, right? So we already kind of saw this in the command line. All this does is makes a bunch of A's. So that's the first part of our exploit. Second thing is we're just writing our the address of the function that we're trying to call. So this is the same number we got out of GDB. And here's where things get a little bit weird. So this is the code that's taking the address of that function, right, the 55555 thing, and it's rewriting it so that it's a little endian representation. And this is basically, think of it as reversing, putting it in the reverse order. And that's basically the syntax you can use in Python to do that in coding. Then we just take those two things, we take all the A's, and then we take that little endian form of the address, and we concatenate them together. And then we write that out to a file. So one gotcha here that's easy to make is we're writing this out to a file in binary mode. If you do not do that, chances are it will look like it'll get messed up in some way. And again, that has to do with the non-printable ASCII characters. Some of those are control codes, and so if you don't do this as a binary file, it will interpret some of those bytes as like control codes, and stuff will get messed up. So do it as a binary file. Okay, so let's run that script. Training wheels, and that will produce a file that is called trainingwheels.exploit. And if you click on that, it will open up in a view that is called hex editor. And basically what you see here, it's two different representations of the same file. So on the left, you're seeing each byte of the file, one byte at a time in hex. So remember, byte 41, that is capital A in ASCII. So if you go to the other side, when it's possible, we'll show you the ASCII representation. So you see a whole bunch of A's there on the right side. So this is basically an easy way to kind of look at these files that have non-printable bytes, and we can kind of see what we would expect here. So we have 152 A's, right? That's what that is. And then at the end, we have that address we're trying to jump to, and again, it's reversed. It's in little endian format. So basically, this looks as we expected it to. So hopefully everything will work here. So next thing we're going to do is we're going to try to run the exploit and see what happens. So we're going to be doing this in GDB so that we can inspect what's going on. So we use GDB to run the program, and this time we're going to tell it to run on the trainingwheels.exploit file. And if we do that, and you look carefully, you can see all of a sudden we have this message coming out of nowhere. So we've actually managed to get the program to run this function that it was not supposed to call ever, right? By carefully crafting this input that overwrote the stack for it. So like, that's pretty cool, right? Also, this is what you get when you go on Crayon and you ask it for a hacker celebrating balloons, confetti, and fireworks, and a lot of happy emojis. All right. So let's quickly try to take the training wheels off, and we'll write what I'll call a real exploit. So most of the time when people think of control flow exploits, they think of spawning a shell, which is a program that lets you run whatever programs you want, right? And that's attractive for kind of obvious reasons, right? It gives you a lot of power and a lot of control. So what we're going to do is before we were basically returning to this function that was already in the program. There's probably not a function already in the program that does this. So what we're going to do is we're going to get some machine code that basically knows how to run a shell. And we're going to put that on the stack, and then we're going to return to that address onto the stack. And that should hopefully write a shell. Where do you get this magical shell code? Well, you can write it yourself, or there's lots of resources to look this up. And my computer is really slow. Should have keep that Chrome running. But this is the shell. I don't want to look at my mail right now. As soon as this loads, this is the shell code that we'll be using. You can see it's for Linux, and it's actually going to bind a shell, which means that it's going to listen on a network port. And we're going to connect in and basically send it commands, and it's going to run them. So here's what the shell code looks like. The one thing I'll point out here is that, again, we have some of these non-printable bytes. So if you need to represent a non-printable byte, you can use an escape code. So \x02 basically means the byte 02, because that doesn't correspond to a letter or a number or anything normal like that. One of the things that's kind of weird about shellcode is that it's this kind of magical string. But really the way to think about it is the processor is going to see that those string of bytes, and that's going to interpret it as machine code. So here's actually what that shellcode looks like if you were to disassemble it, which is basically interpret it as machine code. And you can kind of see it's doing a bunch of stuff on the stack, and a lot of what it's doing is doing these system calls because it's going to open up a network socket, run binsh, and so on. But there's a lot of details there we're not going to go into. So the game plan here, kind of thinking about our stack framing, the way that we want it to look, is we're going to put our shell code at the start of the buffer, right down here. We're going to overwrite the saved return address with the address of the shell code, basically wherever that shell code is sitting. And then in the middle, we're just going to put some A's because we don't really care what goes there. All right? Oh yeah, to do that, we need to find the address of the shell code. So you can do that in GDB. So let's do that real quick. We're going to run the program. We're going to break in the read input function because that's where the buffer variable is. We're going to run until that point. And then we will print ampersand. Ampersand just means address of. So basically tell me the address of the buffer. And we get this weird number ending in DF70. I think you could also have just gone up and look at the message above, where we're also printing the same thing out in the program. So that is the address, basically where our buffer is living in memory. And so that's where we're going to want to return in our exploit. You can see this can vary a little bit on different machines. So this is one thing, if you are following along, you definitely want to see what that number is on your machine. And you're going to have to update that in the script that I'm about to show you. And I'll show you where. So here's the final script for making this exploit. We're going to start with our shellcode. That's going to be the first thing we have in there. The next thing we're going to do is we're going to figure out exactly how many of those A's we need to have, basically to make sure that we're going to put the address of the shellcode at the right place so that it overwrites the saved return address. This is basically just kind of getting the right number. Here's where you may have to adjust that address, right, if it's different on your machine. And again, we're going to do the conversion of that address into little endian form, basically reversing the bytes in the opposite order. And then we put those three things together. And we write it out to a file. This time I call it shellcode.exploit. So let's run that and hopefully it will work. All right, so we've run shellcode.py. So you can open up, here's what that looks like. Looks like a little bit different than the other one. You can see that all these kind of more numbers that are changing a lot, that's the shellcode. So let's try and run this. So we're going to run in exploit me. We're going to run on the shellcode.exploit file. And it doesn't crash. It didn't crash, that's good. Also, VS Code is telling me that I have a new application running on port 4444. This is kind of strange, but a good sign in this case. And so now we're going to open up another terminal. So basically use the plus button there for that. And we're going to use a program called Netcat, which basically connects to a remote port. And so we now have a connection to that remote port. And if I start typing commands, I should start to see the output of those commands. So I'm now basically sending commands that are going to the shellcode that's running inside of that process that we sent the exploit to. And it's now running in that context. So if that was on a remote machine, I would have access to the remote machine. If that is running as a super user, I would be a super user. I can basically do whatever I want now in the context of that remote process. So again, super happy interface. That's pretty neat. So I'm basically out of time. So I will say that there's a lot of stuff that I skipped over here, but it's kind of hard to learn this topic because there's so many more defenses that have been added since basically these exploits were invented. So some of these are stack cookies, ASLR, and dep. And basically in this dev container that I've made, these are all turned off. So if you want to do this for real, there are definitely some extra hoops that you have to jump through. But I will not be talking about that today. Anyway, if this stuff seems cool to you, and it should, take a look at the GitHub repository, and I have some other learning resources for what to do next. But other than that, we talked about a whole bunch of stuff. And if you have questions or able to follow along, I'd be happy to answer that. We're basically out of time. So let me know if you have anything you want to know more about.
Could you give us some Linux commands we could try sending?
Linux commands to the
Well,
shell.
I mean, you just say some Linux commands here on one of the slides.
Yeah, I mean anything you want really. It could be ls, it could be who am I, you could cd, change directories. Basically it's basically just, you can choose at that point. You have access to run whatever, program in the shell that you want.
Apt install Docker, Docker install malicious code.
There you go.
Okay, that was what I was looking for.
Yeah.
So this is a lot easier because you have access to like the source code and the debuggers.
Yes.
How do, just very high level, how do you discover this stuff without any of that?
Yeah, that's a really great question. So one of the most practical ways of doing that is something called fuzzing, which is basically sending either like random or kind of mutated data to a program and just seeing if it crashes. So there's kind of more advanced ways of doing that. Some of those are in my research area, but like fuzzing, if you kind of want to find your own, that's definitely the way to go. So you can look up AFL is a pretty popular fuzzer these days, and it turns out like they're kind of ridiculously effective. Yeah.
Could you go back to your last slide with the resources that you had?
Yeah. So yeah, I don't have the URLs on the slide because I figured it would be hard to type, so I just have to link to the repository and the QR code. So yeah, definitely check those out if you want to learn more.
Have you looked into any of the speedrunning communities for games?
Not a lot, but I've some of the Reddits that I read, occasionally they will post some things about speedruns, and I gather that basically what's happening is there's a vulnerability that can only be triggered if you take certain actions of a certain frame.
Very often, yes. So it's Stack Overflow as well as misconstruction, or just you're going so fast that you clip past a death barrier. It's a combination of aggregate research or accident, and then you have people who obsessively play the game on repeat, and then, oops, I pressed A twice here, and it does a thing it really shouldn't do, like execute arbitrary code. So in Super Mario World for Super Nintendo, they perform a stack overflow by carefully bopping shells and things all over the place, arranging sprites, and it puts all this code in memory. And when they do the final execute, it just warps you to the credit screen because that's the function address. So that was carefully constructed and debugged and reverse engineered.
Yep.
But the fuzzer tools are one thing. What I was really wondering, how do you start enumerating the internal functions, particularly if you don't have direct access to the executable?
If you don't have direct access to the executable, usually the first thing that you have to do is find a vulnerability to weak memory. A lot of times, like in browser exploitation, that's the first thing they have to do because one of the defenses I didn't talk about is ASLR. So you basically don't know any of the addresses that we kind of just assumed we had access to, but a more extreme version of that is not only do you not know the addresses, you also don't know the contents of the code. And if you have a weak vulnerability, you can basically leak the program, one byte at a time to find the machine code.
So in the instance of gray hat or white hat, I have an executable that was programmed by someone who completely abandoned the project and they lost their hard drives. And I legitimately just want to enact some of the internal functions that they never made public, but they know are there. That would be the kind of scenario trying to find executable code to trigger using an external command line tool and then reverse engineer it to re-implement it instead of literally hacking